Hello. Yes, hello.
Okay, so welcome back everybody, and let's continue with the second session of this morning. And the first speaker is Aninda Sinha from the IIS in Bangalore, and he's going to talk about crossing symmetric dispersion relations.
Okay, can you hear me? Yeah, okay. So first let me begin by thanking the organizers for organizing this very bold and wonderful conference and inviting me to give a talk here. So when they told me that I would be on the last day, I just kept telling myself, psyching myself up that all that I need to do is stay alive. And so I thank them for keeping us safe. So I'm going to tell you about crossing symmetric dispersion relations. And this is work that we have done over the last several years in collaboration with students, Ahmadullah and Parthiv. Parthiv is there in the audience. Ahmadullah will be applying for a job this year. He's a very, very bright student, so I urge you to be on the lookout for him. Postdocs, Prashant Raman, who's also going to be in the job market this year. He's also extremely good. Shubham, Kaushik, Shudip, and friends Rajesh and Anyase. I'll briefly mention some work that is relevant for this. The crossing symmetric dispersion relation began, or we started thinking about the crossing symmetric dispersion relation because we wanted to provide a derivation of what is called the Polyakov bootstrap in conformal field theory. And so what it accomplishes is it completes a program that we started with Rajesh around 5-6 years back. And it has also been instrumental for a lot of my hair loss. So let me begin with the string theory motivation. This is not the actual motivation. The actual motivation about the Polyakov bootstrap I'll come to right at the end. Let's start at the very beginning. So one thing that we learn when we do a first course in string theory is how to calculate tachyon scattering amplitudes in bosonic string theory. So for example, suppose you're doing the calculation in closed string theory, you'll get an answer which is should be familiar to all of you. It's a ratio of gamma functions. It comes because you have to do an integral over the location of the fourth vertex operator. But to go from this integral form to the gamma function form, you require analytic continuation. So one question that you might ask is there a way to go from this form to this form without this analytic continuation? And this question was addressed by Ashok Sen in 2019, where he showed how to do this calculation without the need for this analytic continuation. And this leads to a 3-channel Feynman diagram-like picture plus contact diagrams. Now, this is something that may not be familiar to you, so I will go over it. Although I should say that this was, if you open Polchinski's textbook and go to chapter 9, this is already indicated there that such a decomposition is possible. So the way that it works is that you start by constructing the sphere diagram using a procedure called plumbing fixture, where you take 2 spheres and glue them together. So you choose 2 spheres and choose 3 vertex operators. The second sphere also 3 vertex operators, and then you glue them. This should be reminiscent of the S-channel exchange diagram like this. So what you do is you make a choice for local coordinates. So this is a particular choice. This choice is given in Polchinski's textbook. The only thing that you need to remember is that there is a parameter here, lambda, which does not appear in the final answer for the amplitude. So you should ask, what is this parameter lambda doing there? I'll explain that in a bit. So after you make a choice of these local coordinates on both the spheres, you you have a gluing condition, which is given by this equation, and the modulus of Q in this gluing condition ranges from 0 to 1. So the 3 different ways of gluing actually gives you the 3 channels, S, T, and U. And after you're done with this gluing, what you can do is you can do a further Mobius transformation that fixes 3 of the vertex operators at 0, 1, and infinity. And the 4th one becomes a function of this Q. So at this level, what you do is you ask the question that in the complex sigma plane, how much of the complex sigma plane do you cover when you dial sigma Q from 0 to 1? So the answer is that using just these 3 channels, you do not cover the entire complex plane. There is a white region that is left over. The colored regions gives rise to these 3 channels, but the white region is left over, and the interpretation is that the white region generates these contact diagrams. So what Ashok showed is how these 3 channels, explicitly you can do numerical calculations, how these 3 channels emerge as boundary terms in these colored regions. When the dust settles, you have a decomposition of the tachyon scattering amplitude in the following way. So the 3 colored regions gives rise to the 3 channels. So the 3 channels explicitly have poles in all 3 channels. And there is this piece that depends on lambda. And the bulk contact integral can be written like this. So what must happen is that this lambda dependence from the bulk contact integral should cancel off, and you can be left over with an entire function piece, which I'll refer to as a polynomial. So the interpretation of this lambda dependence in the choice of coordinates is that this arises due to the field definition ambiguity that you have in any field theory, in any string field theory. But the final answer is lambda independent. So one question that you get asked at this stage is, suppose you were given just the poles in the S channel, can you fix the rest of the pieces? So how would you go about doing that calculation? So what I'll do now is I will show that this the entire answer can be bootstrapped using the crossing symmetric dispersion relation. So what is the crossing symmetric dispersion relation? So what it accomplishes is that it makes a connection with this Feynman diagram-like picture that the string field theory calculation teaches us, but also has surprising connections with an ancient area of mathematics called geometric function theory. So the next couple of slides will be a little technical. So what I just want you to remember is that since I'm going to have inbuilt crossing symmetry, I have to sacrifice something. And what I will sacrifice is I will sacrifice manifest locality. So let's go about talking about this crossing symmetric dispersion relation. So since some of you may not be aware of what a dispersion relation is, let me just spend 30 seconds explaining. So a dispersion relation is basically a fancy application of Cauchy's residue theorem. You start off by calculating the function, say, at some arbitrary point here, and you deform the contour and make it wrap around the cuts that you assume, or you have to make some assumptions about the analyticity property of the function. And if there are cuts, the contour is going to wrap around the cuts, and what you're going to do is you're going to pick up the discontinuity across the cut. Also, you have to make sure that the arcs at infinity die off, and then you'll have a formula for the amplitude in terms of the discontinuity across the cut. So that's basically the 30-second summary of what a dispersion relation is. So you can do that. So the usual dispersion relation that we usually write down is what is called the fixed T dispersion relation. So if you have a massive scattering amplitude, S plus T plus U is 4m squared. So we will just shift S, T, and U so that S1 plus S2 plus S3 is 0. And the idea is the following. So we start off by having an amplitude that's a function of two variables because of this constraint, S1 and S2. And you could write down a dispersion relation by keeping S2 fixed. So S2 is like what I call T, and you write down a dispersion relation in S1. But when you do that, you lose manifest crossing symmetry. So long time back, people thought about how to write down a dispersion relation that maintains crossing symmetry. So this is a literature that is not very well appreciated. So in fact, I'm going to build on a work that was first done by Oberson and Khoury in 1972. When we located the paper, this paper only had 8 citations. So this actually shows you that don't worry about it. If your work is solid, somebody is going to pick it up later on. So the idea that Oberson and Khoury introduced is that you have to keep something fixed because we want to write down a dispersion relation in one variable. We do not want to write down a dispersion relation in 2 variables. That is also possible, but that is more complicated. So what you do is that you hold something that is made up of crossing symmetric objects fixed. So S1, S2, S3 is obviously permutation invariant, and so is this object. So this is the cubic invariant, which I will refer to as sigma 3, and this is the quadratic invariant, which I will refer to as sigma 2. So one way of solving these two constraints simultaneously is to say that Sk is given by parameterized by this new variable that I'm introducing Z here, and this parameter A that I've introduced here. Zk here is the cube root of unity, and you see the cube roots of unity appearing in the solutions to these two constraints because you have 3-channel symmetry. Suppose you had 2-channel symmetry, you'd see the square root of unity emerging. And in fact, I will show you an example of that kind right at the end. So in fact, you can, I suppose you cannot do this in your head, but then if you plug it in, you'll see that both these constraints are satisfied. And so instead of this cut S plane that you get, you have a cut Z plane. So what happens is that the cuts in the 3 channels get mapped to arcs on the unit circle. And we are interested in what is happening inside this disk. So we have introduced new variables, Z and A, instead of S and T, and we will think of the amplitude as a function of Z and A. Another important point to note is that these two crossing symmetric objects that I've introduced, sigma 3 and sigma 2, have a very nice, simple form in terms of Z. So first of all, the Z dependence is same in both the cases. It's Z cubed over Z cubed minus 1 square. And only the A dependence is different. And you will only see, if you have manifest 3-channel crossing symmetry, you will only see Z cubed appearing. So you'll never see Z making an individual appearance. Only Z cubed appears. And I have indicated here that these are extremal functions. I'll explain why these are called extremal functions. This is a parlance from geometric function theory. In fact, these are what are called Kobe functions in geometric function theory. Okay. So when the dust settles and you're writing down a dispersion relation that is manifestly crossing symmetric, what does it look like? So first, let's assume that we are considering scalar scattering, and the scalar amplitude has a fall off which goes like little o S squared, which means that it's less than mod of S squared for large S. So when you write down a dispersion relation, it has got a structure of this kind. So there is one piece in the amplitude. So this is the amplitude. There's one piece in the amplitude that we cannot fix. This is the value of the amplitude at the crossing symmetric point, and then there is an integral. So let's go over the form a little carefully because this will be important. So like I said, that any dispersion relation will be made up of the discontinuity of the function across the cuts. So this is the absorptive part which gives you the discontinuity. So there is some variable that you're integrating over, which I've deliberately labeled as m square. You can call it whatever you want. One thing to note is that if you were thinking about the fixed T dispersion relation, you would expect to see T here, but rather we have this somewhat complicated looking object. The reason why you have this complicated looking object is that when you plug this equation inside here, you get a quadratic equation for S2, which has 2 roots, and you because you have manifest crossing symmetry, you can use any of the roots. So that is why you have this form. So just to remind you, A was this ratio of the cubic invariant to the quadratic invariant. And finally, this absorptive part multiplies the kernel. And this kernel is a very important and very simple looking object. So it is made up of two pieces. This first piece should immediately remind you of the tree-level scattering amplitude in phi cube theory. And the second piece should remind you of the tree-level leading scattering amplitude in phi 4 theory. So it's as if you are integrating over a particular combination of phi cube theory and phi 4 theories with very specific relative coefficients. And then there is some axiomatic stuff that we have to input because we need to expand this amplitude around a certain point. We need to know where we can expand around. So we need to know where the partial wave expansion of the absorptive part converges. For that, we will use the Lyman-Martin ellipse, which enables us to expand around A equal to 0. Suppose you are Taylor expanding this absorptive part around A equal to 0, you'll get arbitrary powers of A. But A was this ratio of sigma 3 to sigma 2. So if you have arbitrary powers of A, you will start seeing the arbitrary powers of sigma 2 in the denominator. And in any local theory, you do not expect to see such negative powers of sigma 2. So this is what gives rise to what are called locality constraints. So these negative powers of sigma 2 must cancel. And so you get, you're paying the penalty that you've lost manifest locality. Now, in the string field theory calculation, I told you that there is some lambda dependence, which was indicative of a field definition ambiguity. So here, the interpretation of the field definition ambiguity is the following, that you can find a decomposition in terms of poles and contacts, which I'll explicitly show in the next slide. But owing to this locality constraints, you can find a different decomposition because you're basically adding a bunch of zeros, and you can change the basis which you're expanding in. So this is analogous to the field definition ambiguity that we learned from the string theory calculation. So what does the tachyon amplitude look like? So this is something that should be quite unfamiliar to most of you because you don't see a decomposition of this kind. So this is the tachyon amplitude where you have poles in all three channels. This is what comes from this phi 4 type piece in the dispersion relation. And this poles in all three channels gets multiplied by an impressive looking object. It's a simple looking object. This notation is that this is a Pochhammer symbol. So Pochhammer symbol means that this is gamma of whatever is sitting inside the bracket plus the subscript divided by the gamma function of the thing that is sitting in the bracket. And one thing to note is that so you're summing over the levels. K indicates the level, the mass level, and you're summing over the levels. Suppose you focus your attention to one particular mass level. I told you that if you do a Taylor expansion around A equal to 0, you start getting arbitrary powers. So for a fixed mass level, you've lost locality. So locality gets restored only when you sum over all the levels. And this also shows you that you require an infinite number of levels to actually restore locality. So now you can compare the exact answer with whatever decomposition that you've found using the crossing symmetric dispersion relation, and they compare quite favorably. Now, one slight technical thing is that for this sum to converge, you require this real part of A, this parameter that I'm holding fixed, this crossing symmetric object that I'm holding fixed, to be less than something. So I'll comment on what this means right at the end. So let's now focus on the kernel. So remember, the kernel was this simple looking object. And now we are going to rewrite the kernel in terms of the Z and A variables, because this has very simple properties. So first of all, it has a very simple Z dependence. So I have rewritten Z cubed as Z tilde, so that I don't keep repeating Z cubed. The variable that you're integrating over sits inside psi, and also in the prefactor here. You're not integrating over Z. So you can focus your attention on what is happening as a function of Z. Now, there are three properties that I want to mention. One of them is obvious, two are not. So one of them should maybe familiar. So the familiar property is given in the second line, where you recognize that this guy here is basically the generating function of the Chebyshev polynomials of the second kind. So the Chebyshev polynomials of the second kind are also what are called Q numbers. So they're the deformations of ordinary numbers. So you can think of this as either in terms of the Chebyshev polynomials of the second kind or in terms of the Q numbers. The other two properties are not that familiar. So the first property is what is called typically realness. It's also called Herglotzness in the mathematics literature. So a typically real function satisfies this condition that the imaginary part of Z times the imaginary part of the function is greater than 0. And this is supposed to be true for the entire complex plane, but then it's sufficient for what I'm going to talk about, that this property holds inside a unit disk. If, in addition to this property, I also restrict that the modulus of psi is less than 1, I will not have any singularities inside the unit disk. So this function is now going to be analytic inside the unit disk, and that will be very important. The third property, which is probably even less familiar, is that the same object, if you do a slight multiplication by 1 minus z tilde, is actually a generating function of the Alexander polynomials for torus knots. And that seems to give rise to a connection with knot theory. So the lesson here in this is that the same kernel is going to make an appearance in many places. And so it's important to make a mental note of all these three properties. So let's discuss some QFT applications. So over the last few years, people have turned their attention to deriving two-sided bounds on Wilson coefficients, which is called the EFT hedron. So for concreteness, let's first consider that we do not have massless exchanges. I will talk about massless exchanges in a bit. So you can expand your amplitude in terms of Wilson coefficients. And again, you'll have, because it's manifestly crossing symmetric, you only see polynomials of sigma 2 and sigma 3 appearing. And the way that you derive two-sided bounds on these Wilson coefficients is that you use, or the standard method is that you use the fixed T dispersion relation. You use the crossing symmetry constraints, which are equivalent to the locality constraints that I talked about. And you use numerical SDPB techniques. Now, the crossing symmetric dispersion relation provides a simpler explanation for the existence of these two-sided bounds, making use of this Herglotzness or typically realness of the dispersive kernel. The way that it works is as follows. So let's go back and look at the definitions. And you can mentally immediately recognize that if you have two functions, f1 of z plus f2 of z, and you're adding them with a positive relative coefficient, then the convex sum of these two functions will again satisfy this property. So the convex sum of typically real functions is again going to be typically real. For this, you'll have to restrict your range of A, and then you will have a representation which in the mathematics literature is what is called the Robertson representation for typically real functions. And this was actually introduced based on work that was done by Wigner. And Wigner published this in a maths journal, so it is not commonly known in the physics community. So the typically real functions have some magical properties. So first of all, when you expand the typically real functions which are analytic inside the unit disk, they satisfy what is called the Bieberbach conjecture, which was conjectured in 1916. And for typically real functions, this was proven by Rogosinski in 1932. So the statement is that if you have the Taylor expansion of typically real functions in this kind, then these Taylor expansion coefficients are two-sided bounded. What is interesting to note is the bound, upper bound is always an integer. Now, depending on whether the coefficient is of an even power or an odd power, the lower bound changes. It can be easily determined. These things are known. Another important point is that the functions which satisfy or saturate the upper bound are these Kobe functions, which I talked about in the very beginning. The sigma 2 and sigma 3 were proportional to these functions. And so if you do a mental Taylor expansion around z equal to 0, you'll see that the Taylor expansion coefficients are 2, 3, 4, etc. So they will saturate this upper bound. So the interpretation of these two-sided bounds is that they arise because of these Bieberbach-Rogosinski bounds. There are several advantages of thinking in this language. One of the advantages is that in some cases the bounds can be found analytically. So for example, the leading couple of Wilson coefficients, if you take the ratio, they are two-sided bounded and you can find exact numbers on both sides. And you can go to the pion bootstrap, which involves solving for the nonlinear unitarity conditions. And you can check whether indeed this is true. And we get all S matrices to respect this. So this is sort of a numerical experimental demonstration of this Bieberbach conjecture, which is now known as the de-Branches theorem from pion bootstrap. So you make these combinations, and you can play around with whatever S matrices you can generate. So I have given the plot for 200 S matrices, and everything respects this. So the solid blue line here is where your chiral perturbation theory sits. So this is, you can think of this as the QCD values. Now, one thing that is curious is that you have an integer here. So you could ask that, does this integer have some more geometric interpretation than naively being just the index of the power of z? So you can construct Taylor expansion coefficients, linear combinations of the Taylor expansion coefficients made from the amplitudes, and you can show that the absolute value of this object here is bounded, and the bound is in terms of the Alexander polynomial at a specific value. And what we know from knot theory is that this specific value is basically the crossing number of the knot of the appropriate knot. And you can compute bounds which are in terms of trefoil knots and pentafoil knots and so on for any value of n. So let me just quickly comment on massless exchanges. So for now, so far we said that we are talking about theories with a gap. But suppose now you want to talk about a situation where you have the graviton exchange. So for example, suppose you're calculating the dilaton scattering amplitude, and in string theory, and you want to do a higher derivative expansion. So this is your graviton pole. This is the leading higher derivative correction that you get. So so I've parameterized this in a manner where this coefficient here is arbitrary. In string theory, the value is zeta 3, which is that. And you can ask, can we use these ideas to bound this? And indeed, you can do that. You again realize that this graviton pole is an extremal function. This is again a Kobe function. So this is going to be, you can add it in a convex manner to the rest of the dispersive part. And you again apply your Bieber-Bach-Rogosinski bounds. You get G4 to be bounded on both sides in this manner. The interesting difference is that unlike the massive case, the bounds now become space-time dimension dependent. Because to find the maximum value of A, I need to tell you where typically realness holds, and where typically realness holds is a function of D. So as D goes to infinity, the upper bound goes to 2. And string theory nicely lies inside. So let me end my talk with a couple of CFT applications. So the first one was the original motivation why we were interested in the problem in the first place, which goes by the name of the Polyakov bootstrap. So I have. Okay, I'll finish in 1 minute. So the Polyakov bootstrap is that if you take the correlation function in Mellin space and take the Mellin transform, then you can write down an expansion in terms of exchange Wheaton diagrams. And so the question that we wanted to address is that, can you fix these contact diagrams? And without fixing the contact diagrams, we weren't finding a particular zeta 3 that is there in the epsilon expansion. So very timely, there's this book that was written in a couple of years back, which has the title In Pursuit of Zeta 3. I've read this book. It's a beautiful book. I strongly encourage that you read it. So this approach, the crossing symmetric approach, actually fixes these contact diagrams and provides a rigorous derivation of the Polyakov bootstrap. There is another application which is work in progress with NESA, where we talk about conformal field theory in position space. So UV are conformal cross ratios. Now you have two-channel exchange symmetry, UV exchange symmetry. You can write down a similar dispersion relation. And again, in terms of this variable, appropriate variable Z, it has exactly the same properties that I mentioned earlier. So we have some interesting results, which we hope we're going to share with you soon. So, okay, so there have been a number of applications. I didn't have time to discuss all of them. There were some applications that we found using the celestial variables as well. But my outlook is that there are certain things that we can learn from string field theory. So you remember that I had to restrict the range of A. So can we actually improve this and make a dispersive integral which is valid for the entire range of A? There are some suggestions from the numerical bootstrap which respects the Frossard bound. I don't have time to explain this. But the bottom line is that this way of thinking about things using the crossing symmetric dispersion relation appears in higher subtracted dispersion relations, which I did not talk about, Mellin space CFT, which I briefly talked about, CFT position space dispersion relation, again, which I briefly talked about, and as well as recent work on defect CFTs, which I did not have time to talk about. Another thing is that the Z variable that I introduced is related by an SL2C transformation to the celestial variable. So maybe there's a connection with that program as well. So similar techniques may be applicable to all these situations. So I'll stop there. Thank you for your attention.
Thank you very much. Are there any questions?
Yeah, thanks for the nice talk. Do I understand correctly? This was tree-level S matrix.
So okay, so I used tree-level S matrix only when there was massless exchange. So when but the rest, when there was massive exchange, it's a non-perturbative representation. So the pion bootstrap satisfies nonlinear unitarity constraint. So that is for anything.
In the analytic structure, kind of including loops.
Yes. So we are assuming that this is maximally analytic. So only there are cuts. Yeah.
Okay.
Yeah. Shota.
Yeah, so for these massless exchanges, how does the result compare with the result obtained from the ST channel, ST cross and dispersion?
You're talking about this one?
Yes.
Yeah, so where I have been able to compare, it seems like this is twice, a factor of 2 stronger than what they have. But I have been trying to chase down that factor of 2, but I can only do it from my side. It's difficult to do it from their side. So if I'm correct, then it's a factor of 2 stronger.
Also had a question about this connection to knot theory. Is there any sort of string theory interpretation for what the knot theory is?
That's an excellent question. So I've been thinking about that. So I don't have. So you require some dynamical way that knots can transition in from one to the other, and that doesn't seem to have been studied that well. So it's so once we have that, maybe one can say some more things.
And the other obvious question is that the string seems to be somewhere in the middle of the out region. So
yes.
you just hope that somehow it should be at a boundary, I suppose.
Yes. So one thing that I used is that I just used the fact that the imaginary part of the partial wave amplitude was greater than 0. So I did not use the fact that it is less than 1. Neither did I use the fact that there are these nonlinear unitarity constraints. So it is entirely possible that when you put everything together, it will be at the boundary, right?
Are there any further questions? Not. Let's thank Aninda again.